Hi, what I have here on the workbench today is a UNI-T MSO5104HD mixed signal oscilloscope. It's not just yet another oscilloscope. The MSO5104HD offers 12 bits vertical resolution and a whopping 1 GHz analog bandwidth with 5 gigasamples per second sampling rate. Thanks UNI-T for providing me the oscilloscope for me to review. I will provide a link to the product page on UNI-T's website in the video description below. If you are interested in learning more about this scope, you can check out the product manual and technical details following the link. For those who just wanted to see the oscilloscope in action, you can actually forward to the section using the timestamp in the video description below, but I do want to spend a few minutes here talking through some of the specs and highlights of the oscilloscope and also briefly compare those to one of its main competitors in the market. Anyway, the MSO5104HD is in UNI-T's MSO5000HD series. In this series, you have the 350 MHz bandwidth version of the MSO5034HD, the 500 MHz version, the MSO5054HD, and finally the MSO5104HD, the 1 GHz bandwidth version we have right here. As a professional-grade test instrument, these scopes are not cheap, unfortunately. The 350 MHz version retails for more than $3,500, and the top-of-line version, which is what we have here, is more than $6,000 at the time of this recording. Of course, this scope is packed with features. Besides the main oscilloscope functionality, it has integrated 16-channel logic analyzer as an option, a dual-channel 50 MHz arbitrary waveform generator, FFT-based spectral analyzer, protocol decoder, Bode plot analyzer, and it even has a hardware frequency counter and a digital voltmeter built in. So what is the main competitor of this scope? Well, at this price point, the MSO5104HD competes favorably against Rigel's MHO and DHO 5104. In fact, many specs are better for the UNI-T in comparison. For instance, the maximum sampling rate is 5 gigasamples per second versus 4 gigasamples per second on Rigel. The maximum waveform capture rate is 800,000 waveforms per second compared to the 200,000 waveforms per second on the Rigel. In some areas, the Rigel has an edge. For instance, the maximum frames of waveform recording is 500,000 frames on the Rigel versus 400,000 frames on the UNI-T. And by the way, that is for the segmented memory feature. And the vertical sensitivity is 100 microvolts per division on the Rigel versus 500 microvolts per division on the UNI-T. Of course, I don't have a Rigel DHO 5104 here in the lab, so the comparison I mentioned here was strictly from the official specifications. Nevertheless, this should give you an idea of how similar scopes on the market today compare with the UNI-T MSO5000HD series. If you have been following the channel, you probably have seen my review of the UNI-T MSO3054X, and that scope is the top of the line in the MSO3000X series. I will actually bring that scope here momentarily. Now, I combed through the specs of both the MSO3000X series and MSO5000HD series, and the main hardware difference, besides the bandwidth, is of course the HD series offers 12 bits vertical resolution versus the 8 bits in the MSO3000X series. The other specifications are actually quite comparable between these two scopes. Now, in theory, I should be comparing the specs between the MSO5000HD series and the 3000HD series, as both are 12-bit scopes. The reason I chose to compare against the MSO3000X series is because, spec-wise, the 3000X series is actually much closer to the 5000HD series. The maximum sampling rate, for example, for the MSO3000HD series is 2.5 gigasamples per second, versus the 5 gigasamples per second for both the MSO5000HD and the MSO3000X. And also, I have reviewed the MSO3054X on my channel, and you can do detailed comparisons by yourself if you also watch that video. Of course, there are a lot of enhancements made in the 5000HD series. I'm not going to give you an exhaustive list. If you wanted to dive deeper, you can refer to the excellent datasheets on UNI-T's website. But here are some of the highlights. For instance, just to name a few, the MSO5000HD has better DC gain accuracy, higher external triggering voltage tolerance, it added additional measurement parameters and timing analysis, and the function generator has higher sampling rate, 312.5 megasamples per second versus the 250 megasamples per second in the MSO3000X and 3000HD series. The MSO5000HD series also added one-wire and I3C or SenseWire protocol and CAN XL protocol decoding capability. For the majority of the features, the MSO5000HD and the 3000X and the 3000HD series are pretty comparable. But the implementation of these features has been revamped in the MSO5000HD series, and additional features have been added. Also, the MSO5000HD series includes protocol timing analysis as well, which is not offered in 3000X or the 3000HD series. Anyway, enough on the specs. Let's actually take a look at the scope itself. For this comparison, I have the MSO5104HD next to the MSO3054X. At the first glance, you can see that compared to the MSO3000X series, the physical layout of the front panel has been redesigned, and it will definitely take some time to get used to. But the layout is actually very logical and quite intuitive. And by the way, the panel layout is actually identical to the MSO3000HD series. Then here I'd like to point out a few of those cosmetic changes. For example, the probe compensation output had changed to the right-hand side of the BNC connectors versus on the left on the MSO3054X. Also, you probably have noticed, although it's a little bit difficult to see here, the logical analyzer input and the function generator output position have been swapped on this 5104HD. You can see here the logic analyzer is on the right-hand side of the function generator output versus on the MSO3054X, the logic analyzer input is actually to the left of the signal generator output. But as I said earlier, these are just some cosmetic changes. In addition to the standard probes, the MSO5000HD series also support active probes, as you can see here from the probe interface, just like the MSO3000X series. Active probes are crucial for measuring higher bandwidth signals beyond 500 MHz. And speaking of passive probes, the passive probes provided with the scope are these UT P07 500 MHz probes, and you get 4 of these. Now, you may be asking, wait a minute, the MSO5104HD is a 1 GHz bandwidth scope, but why the passive probes are only rated for 500 MHz? Well, for a ×10 passive probe, 500 MHz is actually pretty much the upper bandwidth limit. And this is actually largely limited by the physics of the passive probe design, and the input capacitance unfortunately becomes the limiting factor. So for measuring frequencies higher than 500 MHz, you will need either to use coax or an active probe. The scope is compatible with the UT-PA2000 active probe, which has a bandwidth up to 2 GHz. As mentioned earlier, towards the left, here we have 2 additional BNCs, and these are for the arbitrary waveform generator outputs. Hidden behind the cover here, we have a socket for the UT-M15 logic analyzer pod. I'm not entirely sure what kind of connector UNI-T used here. If you know, please drop a note in the comment section below. Unfortunately, the pod is sold as an option, which means you will have to purchase it separately if you need the digital logic analyzer functionality. Also, the pod appears to have some circuitry inside. It's not just a connector for the test leads, as the scope can actually detect whether the logic analyzer pod is present or not. In my opinion, UNI-T should just provide the logic analyzer pod as standard accessories rather than an option, especially for the high-end models. And here's the backside of the MSO5104HD, with a layout more or less the same as the MSO3000X series. Here you have a BNC for external trigger, auxiliary output, and 10 MHz reference input and output. Of course, the specific functions of these ports can be configured in system settings. On the other side, you have a couple of USB host ports, HDMI port for external display, and a USB port for communication between the scope and the computer. The display resolution, by the way, is 1280 by 800, and you also have an Ethernet connector. Like the MSO3000X series, the 5000HD series also has built-in web server and Wi-Fi connectivity, so you can use the browser to control the scope remotely. There are obviously some changes in the case molding, like these cutouts here, and the thermal design seems to be slightly different as well. As you can see, the air is actually circulated from the side on the MSO5104HD versus from the back on the MSO3054X. The tilting mechanism is slightly different as well. Instead of propping up the stands in the front like the MSO3054X, the 5000HD series has 2 rear stands, which has a few adjustable positions, and you can use to adjust and tilt your scope at the desired angles. Alright, time for me to power it on. Now, there's a physical button at the back, you probably saw that earlier, and the button in the front is just a soft button. Now, before I do that, let's actually remove the protective cover on the screen first. For this scope, you will have to remove the protective cover because it's actually not transparent. It has this pattern on it. So if you keep it on, you won't actually be able to see the screen. Anyway, let's remove it. And I just want to show you here, this is a screen protector. You can see it actually is not totally transparent. It has this pattern to it, so definitely you need to peel it off. And just like the screens on the MSO3000X series, this is also a 10.1-inch LCD touchscreen. And if you feel it, there's definitely some coating on it, makes it very smooth to the touch. Alright, since I have both of these scopes out here, let's power them up at the same time and take a look at the boot up time. The boot up time for the MSO3054X is around 27 seconds, so I'm curious to see how fast the MSO5104HD boots up. Now, to be honest, I think the fan used in the MSO5000HD series is actually a lot quieter. I'll confirm that when I power off the other scope a little bit later. You can also see that the 5000HD series do not show the light patterns during the booting process. To be honest, I really don't have a preference one way or the other. Well, let's just wait and see how long it will take for it to boot up. It seems that the boot up time of these two models are actually quite comparable. Now, let me actually power them off at the same time. Looks like the powering off time is also pretty much identical between the two models. Anyway, so what are some of the main advantages of a 12-bit scope as compared to an 8-bit one? While I still have the MSO3054X up here, let me actually show you that. The most obvious answer is that we now have more vertical resolution. Instead of representing the signal in 8 bits or 256 levels, now we have 4096 levels, so obviously you have more granularity. That is actually important when captured signal has high dynamic range. And this is especially useful for doing analysis on rare signals captured via single shot. So let me demonstrate that. So for this demonstration, I'm actually capturing signal on the 3054X. This is a wavelet signal, and you can see here we captured the stable signal. Anyway, so now let me pause the acquisition. And now let's actually adjust the vertical scale. So you can immediately see that the captured signal actually can see a lot of quantization errors. That's because we're capturing the signal using 8 bits. Of course, for repetitive signals, you could just recapture the signal again with the different vertical settings, so the captured signal magnitude can be higher, and therefore you will have more bits representing the signal, and the resolution will be naturally higher. For example, right now if I resume acquisition, you can see that at the same scale, of course, we can see with a lot more detail. That's because right now we're digitizing this section of the signal with all 8 bits. So for this reason, in most cases, you can actually get by with an 8-bit scope, but you will need to set a vertical amplification such that the signal of interest take up as much of the amplitude as possible for the best resolution. And sometimes you may need to take multiple measurements to achieve that. But for transient signals, especially if you are only able to capture that once in a while, it's going to get much more difficult. So pretending this was a transient signal, let's reacquire that. If this was a transient signal, for example, now if you just capture the single shot, and now if you're trying to expand the signal, that's where you lose the resolution because you don't have enough bits representing the signal here. And now let's actually take a look at the same signal on the 12-bit oscilloscope. And here we capture the same signal on the MSO5104HD. So let me pause the acquisition here. And let me expand the vertical. So you can see when we adjusted the vertical amplification, the signal actually appears a lot cleaner on the scope compared to that on the MSO3054X. And that is because for a 12-bit oscilloscope, you have extra 4 bits. Essentially, we'll have 16 times finer granularity. So for the same capture signal, we can actually zoom in further and still have good resolution, as you can see here. So now with the same captured signal, you can actually resolve both the higher amplitude portion and the lower amplitude portion in the same shot. This is essentially the higher dynamic range I mentioned earlier. The second benefit of a 12-bit scope, which a lot of reviewers don't really mention, is that it actually has lower noise floor in FFT mode when doing spectral analysis. Depending on the architecture, you could see 20 decibels improvement in terms of the noise floor. So let's actually verify that. To demonstrate the point, I have enabled FFT on both of these scopes, and both have a FFT points of 32K, and the frequency range is from 0 to 15 MHz on both of the scopes. Let me show you here. So now let me actually turn off the dialog here, and let's actually take a look at the noise floor. So you can see on the MSO5104HD, the noise floor is below 92 decibels. On the 3054X, you can see that the noise floor is actually approaching minus 92 decibels, which is much higher on the MSO5104HD. And also, as I mentioned earlier, the noise floor is also influenced by the architecture. So with the lower FFT noise floor, you should be able to resolve much weaker signals. And of course, because of the smaller quantization steps, you will also have lower quantization noise. So definitely the captured waveforms will be a lot cleaner. By the way, the MSO5104HD also has the enhanced resolution mode, or ERES mode, which can further enhance the vertical resolution up to an additional 4 bits. This gives you a maximum enhanced resolution of 16 bits. Now, this is actually achieved through post-processing, as the ADC is only capable of digitizing 12 bits. As a result, the trade-off of the ERES mode is that the oscilloscope bandwidth is greatly reduced. So let me actually show you that. To get to the setting, you need to go to the acquisition menu. Now, keep in mind, the actual bandwidth is actually dependent on not only just the number of bits, but also depends on the memory depth as well. Let me show you that. So for example, right now, the acquisition mode is normal. And by the way, if you don't want to touch the screen, you can also hook up a wireless mouse, and that is actually quite convenient. But for our testing today, we'll just use the touch screen. Anyway, right now, the acquisition mode is normal. Let's actually select the enhanced mode. So in the enhanced resolution, you can see we can select additional bits. So let's actually do 1 bit. And for the time being, you can see that we don't actually have any impact on the bandwidth. And that's because the memory depth is set to auto. And interesting here about the enhanced resolution is that if you reduce the memory depth, the maximum bandwidth is actually going to be reduced as well. So let me show you that. For example, right now it's auto. And if I select the memory depth to, let's say, 25K, you will see that the bandwidth actually dropped to 18.8 MHz. And if I increase it to 250K, you can see the bandwidth also increased as well. That actually makes sense because we actually need more data points to do the post-processing. So let's actually leave the memory depth as auto, and let's take a look. So for 1 enhanced bit, you can see that we actually don't lose any bandwidth. And let's increase it to 1.5. And we don't lose any bandwidth either. So let's change it to 2 bits. And now you can see the bandwidth immediately is limited to 500 MHz. And as I increase the number of bits, you will see that the bandwidth actually drops even further. So for 2.5 bits, you can see the bandwidth dropped to 160 MHz. And for 3 bits, it drops further to 62.5 MHz. And for 4 bits, now the bandwidth is only at 25 MHz. For the rest of the video, I don't think I'm going to use the 3054X, so let me actually put that away. We'll concentrate on the 5104HD. So with the 3054X out of the way, you can just hear how quiet the MSO5104HD is. It's literally whisper quiet. You can barely hear the fan. Next, let's actually take a look at the 1 GHz bandwidth. Of course, as a lab-grade instrument, I have no doubt of the claimed bandwidth. But what I wanted to see is how the waveform looks at the bandwidth limit and how much margin we actually have with the bandwidth. For this test, I'm going to hook up with my HP8642B in the background in a moment, which can generate sinusoidals up to 2 GHz. Let's actually first change the channel input impedance so that we can match the 50 ohm as what is expected by the 8642B. So to do that, let's actually come to the channel. And you can see here right now the input impedance is 1 megohm. Before we can change that to 50 ohms, we need to actually change it to DC coupling. You can see now the 50 ohms is available. So we can change it to 50 ohms. If you have used the 3000X series scope, you should be very familiar with the setup. But let me quickly walk you through. You can see that you can select whether or not to invert the channel, whether or not to have fine control by default, and the scale, resolution, position, so on and so forth. Of course, you can manually select the probe attenuation. By the way, the UT P07 probes that came with the unit actually can be auto-detected as ×10 probes. And here you have the bandwidth limit. You can see that we have full 20 MHz, which is pretty standard. And then we have this digital bandwidth. The digital bandwidth filter actually is implemented, as the name suggests, in a digital filter, and is applied mathematically in the DSP. The range of this filter can be set between 50 Hz and 1 GHz, which can be used to filter out noise and interference in post-processing. Anyway, let's take a look at RF signal from the 8642B. Alright, right now you can hear the 8642B humming in the background, and currently it's outputting a 100 MHz signal. I adjusted the output amplitude so that it is roughly at 500 millivolts, so that later on when we test the bandwidth, we can easily figure out the bandwidth limit at roughly 350 millivolts. Anyway, I've also turned on the hardware counter. You can see here, it is currently at 100 MHz. Let me just zoom in quickly for you. And you can see in this close-up, we have the measured frequency and also the amplitude right at the bottom. So let me actually increase the output frequency from the signal generator, and let's see what we get on the scope. Because this is a 1 GHz scope, let's actually increase the frequency 100 MHz at a time. So let's do 200, 300, 400, and let me expand the horizontal to the maximum. And let's keep increasing, 500, 600, 7, 8, 9, 1 GHz. And you can see at 1 GHz, we're still at 400 millivolts, so that is still above the 3 dB bandwidth. Now let me increase the frequency a little bit more. Now it's 1.1 GHz, and you can see we're still above 350 millivolts. So let's do 1.2. 1.3, 1.4. So you can see roughly between 1.3 and 1.4 GHz, we actually drop below that 3 dB bandwidth. So right now we're at 322 millivolts. And when we were at 1.3 GHz, we were slightly above 350 millivolts. So that gives you an idea of the general bandwidth of this scope. It's actually quite generous. The actual bandwidth is quite a bit above 1 GHz. And I just want to show you what is on 8642B right now. You can see the current setting is at 1.4 GHz. Now let me keep increasing the frequency and just to see what we get on the scope. Of course, it's already below the 3 dB bandwidth, but we should be able to see whether or not we're actually able to capture that signal. Given the 5 gigasamples per second sampling rate, we should be able to capture quite a bit higher. So let's take a look. So now I'm doing 1.5 gigahertz. And you can see we have no problem detecting that 1.5. The amplitude, of course, dropped quite a bit. So 1.6, 1.7, 1.8, 1.9, 2 gigahertz. And let's actually take it to the maximum, 2.1 gigahertz. That's the highest I can output from the 8642B. I'm actually very impressed because right now we're at 2.1 gigahertz. You can see the capture signal remains very clean. Of course, we're not able to measure the accurate frequency from the hardware counter here, but we still have roughly 150 millivolts of amplitude. So let's actually enable the frequency measurement using the software counter here. And I suspect we would be able to measure the frequency here. So let's come here, measure, and add. Let's see here, horizontal, and let's do frequency here. And yep, you can see the software measured frequency is actually quite accurate, currently at 2.1 gigahertz, which is exactly what we're outputting from the signal generator in the background. As you can see here, that's 2.1 gigahertz. I believe the acquisition architecture is actually very similar between the 5000 series and the 3000X series. So let's take a look if we enable another channel and what we get in terms of the maximum sampling rate. Currently it's at 5 gigasamples per second. So let's enable channel 2. And immediately you can see that actually the sampling rate dropped to 2.5 gigasamples per second. Of course, right now we're not able to accurately measure the frequency because there's some aliasing going on. And that's to be expected because right now the sampling rate had dropped by half. Now let's actually try this on channel 3. And you can see by turning on channel 3, the sampling rate was not impacted. So this tells me that channel 1 and 3 operates independently. Of course, channel 1 and 2 and channel 3 and channel 4, these are two different groups. So if you are just turning on one of the channels in each group, you are able to get that full 5 gigasamples per second sampling rate. But if you are enabling, let's say, channel 1 and channel 2, or channel 1, channel 4, for that matter, or all 4 channels, then you are going to see half of the sampling rate. So let's actually take a look. If we enable both channel 1 and channel 2 at half of the sampling rate, what is the highest frequency we can actually get on the scope? So let's do that. So I'm going to do channel 1 and channel 2, remove channel 3. So let's reduce the frequency here. So now we're at 1.4 gigahertz, and that's actually still not right. So 1.3, yeah, you can see, okay, 1.2, 1.1, so let's do 1.2. So you can see that essentially anything above 1.1 gigahertz, we're not able to reconstruct, but there's definitely no problem with the 1 gigahertz bandwidth. So right now, for example, we're at 1.1 gigahertz, and you can see that we're able to measure the 1.1 gigahertz and also reconstruct the sinusoidal with no problem. So the bandwidth of this scope is definitely quite impressive. And as you have seen, there's quite a bit margin built in. Now let's actually take a look at the waveform of this avalanche pulse generator. I usually use it to verify the analog bandwidth of oscilloscopes, and you have probably seen me using it in pretty much every single oscilloscope review video I have done on this channel. I actually don't quite know the rise time of the avalanche pulse, just because I never had a scope fast enough. Now with this 1 GHz bandwidth scope, I think I may be able to infer the rise time of the actual pulse. And in my review, if you recall, in the 300 MHz bandwidth MSO5304X review, I think I knew I was pretty close to the limit of the avalanche pulse generator because the rise time is just right around the limit of the bandwidth. And on the 500 MHz scope I tested, the obtained bandwidth is actually lower than 500 MHz, so that I know the rise time is probably not that much faster than 1 nanosecond. But this time we actually have a much higher bandwidth scope, so we can validate that. All right, so let me expand on the signal here. And now you can see we have this very clean avalanche pulse. And by the way, let's actually enable the automatic measurement. So let me come here and do measure. And let's do add. Horizontal, I think it's rise time. And let's take a look here. So the measure rise time, I wish you can see this. You can see it's right around 1.13 nanoseconds. So if you do the calculation here, that rise time translates into roughly 350 MHz bandwidth. Obviously, that's not correct because we have a 1 GHz bandwidth scope, and we had validated that with our RF generator. So the limitation here is really with this avalanche pulse generator. As we just verified earlier, the bandwidth of this scope is above 1 GHz. So let's just assume it's 1 GHz. That roughly translates into a 0.35 nanoseconds rise time. So given the rise time of the scope and the avalanche pulses we measured, we can deduce that the rise time of the avalanche pulse is roughly around 700 to 800 picoseconds. Now, a good avalanche pulse generator can probably output pulses much faster than that. So at some point, I may need to tweak the design of the avalanche pulse generator a little bit. In theory, I should be able to reduce the rise time to probably about 300 to 500 picoseconds with better components and probably more careful layout. The memory depth of this oscilloscope is 500 megapoints, so that's a lot of data points you can actually gather. The 5000 HD series has a navigation functionality, which allows you to actually jump to the captured events easily. Let me actually quickly demonstrate that with the avalanche pulse generator. All right, let's go to the menu. And here you can see we have this navigation. That's what we want to select. And before I do anything, let's actually adjust the horizontal so we have more pulses captured. So let's do that. And this is good enough. So now let's actually do search events. And switch on. So now let's actually pause the acquisition. If I go to the navigation menu, you can see we now can actually navigate through different pulses. And of course, we can also search different pulses using the criteria given here. And if you want to see the events captured, you can also turn on the event table. That will show you all the events that captured with different timestamps. Of course, right now, given the horizontal, we only have about, let's see how many events, 11 events. If I reduce the horizontal, if I hit run again, you can see now we're actually capture a lot more because now we actually have a much wider time frame to work with. So let's stop. And of course, right now you can zoom through this. And let's say I wanted to come to this specific event. Now you can see that we actually navigated to that pulse. So it's great that we have a huge amount of sample memory and we can capture a lot of waveforms, but from the capture we just did, you can see that the waveform is actually pretty sparsely populated. Although we capture a lot of events, the majority of the waveform memory is actually wasted because there's nothing interesting between these avalanche pulses. And this is because in standard triggering mode, once the oscilloscope is triggered, it will continue sampling until the sample memory is filled. And in this case, when the signal is sparse, you will end up wasting a lot of sample memory. To solve this problem, modern digital scopes often include the so-called segmented memory mode. The idea here is instead of using a single chunk of large sample memory, the memory is divided into smaller segments or frames. The main difference is once triggered, the oscilloscope will only fill the next available segment instead of the entire sample memory. And once a segment is filled, the oscilloscope will stop capturing and rearm the trigger until the next trigger event occurs. So in this way, even the events of interest are few and far in between, you can actually capture all of them because the events will be individually triggered and captured into its own memory segment. The MSO5104HD can handle a maximum of 400,000 segments. So while in this case, each segment is just slightly bigger than 1 kilobytes, the segment is guaranteed to contain meaningful data. Of course, you can adjust the number of segments based on the signal complexity. So here, let me demonstrate using the same avalanche pulse generator here. Now I just reacquired the signal so you can see the single captured avalanche pulse on the screen here. So let me enable the segmented memory mode. And to do that, you actually need to select the record button. And let's not worry about the fast record here. So let's actually take a look here. You can see that we can actually record up to 400,000 frames. So let's enable it. And now let's say we want to record. Now we can actually replay all the captured waveforms here. So to do that, we can do frame by frame. You can see that. Or you can just let it play. Now, I do wish we can use these multi-purpose buttons to select which frame we're looking at, but you can see that we can actually not use these two buttons to replay the waveform, which is a pity. I hope that UNI-T actually can address this in a future firmware upgrade because it will be much more convenient to be able to use the knobs to actually select different frames. So now we actually captured 1,000 of these avalanche pulses. Of course, we could have captured a lot more, but this is only possible because we're using segmented memory. Without that, you won't be able to do this. So again, I just demonstrated how useful segmented memory is for capturing these sparse signals. I think what I'm going to do next is to show you some of the triggering capabilities this MSO5104HD offers. Here I'm using a UNI-T M13X demo board. I had reviewed this demo board in one of my previous videos, and I will provide a link below. This is actually quite a capable demo board as well. So the first signal we're looking at here is a round pulse. And right now we're just triggering by edge. Of course, we are not able to totally stabilize the signal because even though we have this trace that is somewhat stable, but there's some garbage displaying in the background. So the goal is actually we want to obtain a stable triggering. So let's take a look at how we do that. So for that, I'm going to come here. You can see these are our triggering options. Currently, we're doing the edge triggering. And if you drop down here, you can see we have a plethora of different triggering options. I won't be able to go through them one by one, but you can see here we can do edge triggering, delay triggering, so on and so forth, triggering on different protocols. And one of which you can see is round. So this is a pulse we're trying to capture here. So let's take a look. And for the round pulse capturing, obviously you can set a high level. And here, let's actually set high level to be 450. So let's do this. So that's our pulse. So that's for the higher amplitude pulses. And now we have a low level. So the low level here, actually, let's do maybe 250. Now we have the interval, and you can see here roughly per division is about 500 nanoseconds. So let's actually increase that. And you notice that at some point here, we actually are able to trigger it stably. So let's actually go back and let's take a look at the trigger signal. Of course, that's just a demonstration, and now you know how to trigger on the round pulse. And there are, of course, other techniques. I'm not going to go through them one by one. Trigger by region is probably the most versatile triggering option offered by MSO5000 series. Actually, I have demonstrated this on the MSO3054X, but here I'll do the demo again, because this functionality I think is definitely worth mentioning. And the test signal we're generating here is the so-called non-monotonic signal. And this signal has some defect, but you can't really see that. And I want you to pay attention to this area. Once in a while, you can see a glitch. Yeah, you just saw that. And that is actually the signal we're trying to capture. Of course, it doesn't happen very often. It happened again. And to capture that, what we want to do is we want to actually trigger on that region. So what I do here is I will draw a region here. And I want to say whenever it crosses that region, I want to trigger. Yep, you can see now the signal had crossed this region and we get a stable triggered waveform. And I just zoomed in a little bit. You can see that this signal is actually kind of odd. Instead of having a smooth rising edge, it actually curves quite a bit. So we're actually triggering on this very odd shaped rising edge. And without this triggering by region capability, it's actually going to be impossible to trigger on this signal. This kind of trigger is actually not new on this MSO5000HD series. I should note that this functionality is actually not new on this 5000HD series, but the functionality had been significantly improved. For example, in the past, you can only draw the rectangle and you cannot really precisely adjust the region. But right now, this feature has been improved. You can actually set the region very precisely. So let me show you that. So for example, you come here, you can go to the menu. You can see that if you want to adjust the region very precisely, you can actually do so manually. For the next demonstration, let's actually take a look at the protocol decoding capability. And for that, I'm going to decode a UART signal generated by the M13X demo board. So here I have a UART signal. Let's take a look at how to decode that. So here I'm going to come to the menu, and we're going to select the decode functionality here. So for this, let's actually try to trigger on one of the characters here. I do know there's a hexadecimal character that is 80, so let's actually trigger on that. So come to trigger. You can see the bit rate is 115,200, and that's correct, but the data bit is actually incorrect. So we actually have 8 data bits, and the trigger here is 80. So I think that should be sufficient, and let's actually take a look. Oh, by the way, let's actually display that. So let's go back and let's come back here. So we wanted to display the decoded signal here. And you can see, by the way, this trigger we just set up. And let's take a look here. So you can see, indeed, we're triggering on this hexadecimal 80. And here is the stable signal. Now let's actually take a look at the built-in dual channel function generator. To enable them, you just need to press on either G1 or G2. These are the two function generators. So here's G1, here is G2. I should mention though that the arbitrary waveform generation capability is actually an option, so you have to enable that before using it. If you don't enable the option, you only get a function generator, and of course there is arbitrary waveform generation capability if you enable the option, but you have to pay extra for that. I think out of the box, it gives you a few weeks of trial period. Since I did not enable the arbitrary waveform generator, what we're looking at here is essentially just a function generator. But even function generator, you can see is actually still pretty good. We have continuous waveform. You can see here, you can do AM, FM, ASK, FSK, and sweep. So let's actually take a look at a sine wave. So let's generate, let's say, a 1 megahertz. Let's actually enable it. So let's acquire the signal. And you can see this is our sinusoidal. Then you should be able to adjust it. And you can see that it's actually adjusting real time. And here you're looking at an amplitude modulated signal. The carrier frequency is 1 MHz with a modulation frequency of 1 kHz, and the modulation depth is 100%. You can see that the signal looks very nice. In fact, we have this gradient going on. A lot of the scopes call that ultra-phosphor or whatnot. And you can see that we have this intensity grading on the waveform here. You can actually adjust the intensity grading. Let me show you that. So I think you come in here, and it's display. Yep. And you can see we can actually change the brightness here. So if I change the brightness, if I make it darker, you can actually see the intensity grading a little bit better. But anyway, let's go back to 50%. And you can also change it to color. So this way it actually cycles through different color palette, depends on the intensity, and so on and so forth. And here is an FFT of that amplitude modulated signal. You can see here the center frequency is at 1 MHz with a frequency span of roughly 20 kHz. And you can definitely see the modulation envelope here. And of course, I had enabled waterfall display, so you can see the spectrum up there as well. And on the left side, you can see I also zoomed in the waveform. Of course, this window operates independent of everything else, so you can choose to, for example, zoom in your signal. Now you essentially have two displays. One has the zoomed in version, the other one has the original waveform. So of course, you can adjust the zoom here as well. So this actually comes in very handy if you are trying to do some analysis on the signal and you can't quite see what is going on. So this zoom will give you a little more detail. And let's actually take a look at the sweep as well. So let's adjust to sweep. And now we're sweeping between 990 kHz to 1.01 MHz. And you can see that we're scanning through this frequency in about 10 seconds. And let's disable that. And right now you can see the spectrum move across the screen here. And of course, we have two signal generators built in, so we can display laser rule figures with no problem. And right now you can see we have put the scope in XY mode. So to control that, you can come here, and you can see here we change to XY. And the two signals are essentially 90 degrees apart. You can see here. So the first signal is sinusoidal at 1 kHz, and the second one essentially is the same 1 kHz signal with a 90-degree phase shift. So that's a perfect circle. Now let's actually adjust one of the frequencies, and you can see, hopefully you can see. So let's actually, by the way, you can use this encoder here to actually switch to different digits. So let's try adjust this one, and you can see that we actually are able to generate different laser rule patterns. Of course, you can also enable the cursor, and that will tell you the measurement here. And you can see that all the measurements are essentially displayed here. Just like all the other UNI-T scopes I had reviewed on the channel, you can hook up an external monitor to monitor the waveform. Essentially, it duplicates the display. And also you can control the scope via a browser on your computer. And because the 5104HD supports wireless, so you can control the oscilloscope wirelessly. There are a ton of features, of course. I can't possibly show you every single one of them. If you wanted to get a sense of all the features this scope has to offer, you can check out my review video of the MSO2304X. As I mentioned at the beginning, the feature set of that oscilloscope is actually very comparable to the MSO5104HD. There are some extra features on the scope that is not available on the MSO2304X, and I had pointed them out earlier. And if you want to dive deeper into doing power analysis of the scope, you can check out my MSO3054X review video. And also I had recently done a video on doing Bode plot with the MSO3054X. I'll leave a link to that video in the video description below as well. If there's anything else you want me to show you and there's a feature you want me to demonstrate, please be sure to leave me a note in the comment section below, and I might do a separate video on that if there's enough interest. And that's all I wanted to cover in this video. The UNI-T MSO5104HD is a very capable 1 GHz bandwidth 16-bit oscilloscope. If you enjoyed the video, please remember to give it a big thumbs up and don't forget to subscribe to this channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.